Okay, everyone, welcome. This is going to be the second segment of the electronics course that we're doing. And what we're going to look at today is the p-n junction. So what do we do with the p-type and the n-type material once we have it made? Okay, what we're going to do is we're going to take a piece of n-type material, and we're going to take a piece of p-type material. So these are pieces of semiconductor material that have been doped. The n-type has been doped with impurities that have 5 electrons. The p-type has been doped with a material that has only 3. We call these pentavalent impurities. Pentavalent. And the materials that we use for doping the p-type material we call trivalent. Trivalent. Now, once we have these two pieces of material, what we do is we take them and we fuse them together. And the way we do that is like this. And there's the junction right there. Now, once these have been fused together, something very, very interesting happens. Now, the n-type material, remember, is n-type material because it has more electrons. And so I'm going to show these electrons in this way. Now, obviously, there's a lot more free electrons in here than what I'm able to draw here. But I'm going to draw these just like this. And I'm going to put a negative symbol in there to show you that they're electrons. These are all electrons. Okay? Now, there's no flow here because there is no connection on either end of this. There's no voltage to cause any flow. So really all we have is here we have a piece of material that has a bunch of surplus electrons. And over here, something interesting happens. Over here, we have some spaces or some holes. And these holes would nicely accept some free electrons if there were any to be had, but there aren't. Okay, because all we have is these two pieces of material. So what we have is in the n-type material, we have some surplus electrons. In the p-type material, we actually have a deficiency of electrons. Now, here's where the really interesting thing happens with this material. As soon as we've actually fused this together, a very interesting interaction takes place between these two materials. This electron right here, closest to this junction point, okay, this is the junction right here. There's the junction, and the electron that is the closest actually goes like this. It jumps across into here, into that hole. And this one jumps across into this hole. And this one jumps across into this hole. And this one jumps across into this hole. Now, as you can imagine, what happens is if an electron moves from here and it moves into this space, in fact, what happens is now this whole area right here has become neutral. In other words, these electrons have gone from being free electrons to filling into these holes. And what we wind up with is an area right here that has a net charge of 0. And this section in the center has a specific name, and this is called the depletion region. Depletion region. Now the depletion region is essentially depleted of any charge, either positive or negative, because the electrons have satisfied the basically the the positive charges that were there, which were actually spaces, and so everything is filled in and it's become neutral. Okay, now to continue on, what we have is, now that we've actually created this neutral barrier region, it's also called a barrier region because it's a barrier to essentially to current flow. What happens next is that if you look at these free electrons that are still left on this side, and they look over here at this side and they go, I wonder if I could make the leap over to there. And in fact, they can't, because once you've actually established this depletion region in the center, it's wide enough, it's like an insulating layer. And so it's like actually, it becomes like an open switch, okay? It becomes like an open switch. And so these free electrons are pretty much isolated on this side. These holes over here are isolated on this side. And what we have then is really just this depletion region that is there, and nothing can actually flow through it. Okay, so here's what happens now. Now that we have this, it's called a PN junction, basically. And that's really just because of the two types of material that are put together. What we're going to need to do is, in order to use this as a diode, another name for this is we need to attach some leads. Now, the leads that are attached are given names, and the name is a constant, okay? In other words, the name for the lead that is attached to the N-type material will always be the cathode. Always be the cathode. And the lead that is attached to the P-type material will always be called the anode. Now, we may hook up the cathode and the anode using different polarities of voltage, but the anode is always the P-type material, the cathode, the N-type material. Okay, so let me show you the symbol for the diode. Looks like this. Now, in this side of the diode, we know this is the N-type material, this is the P-type material. I just want to show you. Sometimes it's a little harder to remember exactly how this is done. So just think of it like this. Think of this as your diode symbol. This is your cathode here. And then over here, this is your anode. And so when you see a diode symbol, which in its short form basically looks like this, then you can actually see this as the K, see this as the A, and you know that this is always going to be your N-type material. This is your P-type material. And so it makes it easier when you go to bias this or connect it up. It gives you a good idea what you're doing in terms of current flow. Okay, what we're gonna talk about now is once we have the diode sort of put together and built. We have the anode and the cathode, and we want to know when we place this into a circuit, we have to look at the connection as to whether it's going to block or conduct. And so what we call this is biasing. So depending on how we connect the source of voltage to the diode will depend whether it blocks or conducts. Let me explain exactly how this works. Now, if you take a diode, and I'm going to draw this out in the form that I just showed you. Here's the two pieces of material with the leads on. This is going to be the anode, which means that this is going to be the p-type material, and this is going to be the cathode. I'll explain why I use a K for cathode in a little bit. Just keep watching, and that'll come up. Basically, this is going to be the N-type material because the cathode is always the N-type material. The anode is always the P-type material. Now remember, at this point, before we actually connect a source of voltage to it, what we have is a neutral barrier region. And here we have a bunch of free electrons, like this. And over here, we have a bunch of spaces that would accept electrons, okay? So that's what we have as it is. Now, let's go ahead, and I'm going to show you forward bias first. And what forward bias means is that we take this and we connect it to a source of supply. Now, you can't just connect a diode to a source without putting in some resistance. Otherwise, you're going to have a short circuit. So this is going to be the what I'll call the load resistor, all right? And the source is going to be right here. This is going to be a DC source. And forward bias means that I make the cathode negative. So this is going to be the negative, and this is going to be the positive here. The positive will go to the anode, negative will go to the cathode. And this arrangement is called forward bias. Now, exactly what happens inside that PN junction when we do this? Let's take a look. Imagine that when I basically turn this source on, what I have is, if this is negative, imagine a lineup of electrons on this side. Now, when electrons come in close proximity to each other, what will these free electrons do if all of a sudden you have a source of electrons being pushed into this lead? Well, we know that if we have two negatives, they actually push apart from each other. And so what that means is that all of these negatives are going to start moving this way, and they're going to start to cluster over close to this edge. And if we make this positive, I'm going to show this in this way. Imagine a bunch of spaces, and they're actually lined up on this side. And these are really the holes, right? And so if we have a bunch of these here, how are they going to interact with these? Remember, these are these spaces we can show as a positive. Well, that means these are going to repel from these. So here we have this, and they're repelling. So that means that these holes here are going to move in and cluster over this way. Now, as we raise this voltage, these will push closer this way, and these will push closer this way. And when we reach a certain voltage, this region will have been squeezed down to the point where it's like this. And at that point, all of a sudden, these can move into this space. That depletion region has been basically closed, and now we actually have like a closed switch, and the current will begin to flow through this junction. Now, how much voltage does it take? How much voltage does it take to actually to take that depletion region and close it. And we call this barrier voltage. Barrier voltage. And with silicon, that voltage for a PN junction is 0.7 of a volt. Okay, 0.7 of a volt, and that's what we call barrier voltage. And many of you will remember that number from previous experiences with diodes. Now, once this is closed, then we'll have current flow that will be based on the amount of voltage and the amount of resistance, and this voltage will just stay constant. As the current flows through, this voltage drop does not go any higher than 0.7 of a volt, and that just maintains as a closed switch. And so forward bias means that we've closed the switch, and now we're going to conduct with just that barrier voltage drop being maintained across the diode. Okay, let me show you now reverse bias, okay? Here's what happens with reverse bias. We take the same PN junction, and we start off with our depletion region. Now remember, if you have not yet applied voltage, all you have is these two pieces, and you have that depletion region in the center, which is kind of neutral, right? Now here we have the terminal that we'll call the anode. Here we have the terminal that we'll call a cathode. And what we're going to do this time is we're going to make sure that we place our load resistance in. And that's there to make sure that we don't have a short circuit once we turn the supply voltage on. This is my DC voltage. Now, as you can see, the anode is still, the anode's the anode no matter what. So this is the P-type material. Cathode is the cathode. So this is the N-type material. So the cathode always connected to N, anode always connected to P. So what's really different about reverse bias? Well, reverse bias means that we actually apply the opposite voltage to the diode. And so that means that now in this instance, I'm actually going to make this terminal positive, and I'm going to make this terminal negative. So I've switched the polarity of my source. Now let's take a look at what happens up here in the PN junction. Now remember, what do we have in this side? Well, we have a bunch of free electrons in this material, and they're just kind of sitting there, static in position. What do we have in the P-type material? I'm going to show them as plus signs. These are really holes, okay? They would accept an electron nicely if there was one to be had. So there we have the material. Now, what we're going to do in reverse bias is we are now going to have a lineup of electrons on this side, and we're going to have a lineup over here of holes. And so interestingly enough, what's going to happen, now we know that unlike charges are going to attract, and so here is what happens to the material. These electrons go, wow, there are positive charges or holes, and these electrons all cluster over to this end. They all disappear. They move as quickly as they can from wherever they are located in that N-type material, and they move over here because we have now this huge attraction between the positive and the negative. And the same thing happens over here. We've got a bunch of electrons lined up over here, and they are going to strongly attract all of these positive charges or holes, and they're going to cluster over here like this. And they're going to move from here to here. Now, effectively, what just happened? Well, we have taken this barrier region and we have expanded it to here. And now what you can see is a large open switch, okay? We call this an expanded barrier. And this is like now an open switch, fully open switch. And in most diodes, the voltage, we call this the reverse blocking voltage of a diode, or the PIV, peak inverse voltage. It's the amount of voltage that you can apply to it in reverse bias, and before it breaks down. That voltage typically can be in the hundreds of volts. Okay, the diode we're going to be using in our lab experiments, I believe, is rated for about 600 volts. We'll be looking at that in our data sheets when we get there. But the peak inverse voltage can be a very, very high level of voltage. And so this space here from anode to cathode is capable of blocking against a very large amount of voltage. No current flow will be allowed. So once that's open, reverse bias, open switch. Okay, now we're going to put the diode in a circuit and we're going to see how it behaves, all right? So what we start with is I'm going to put a source over here. This will be DC. This is going to be negative, positive. And I'm going to move along here. I'm going to show, first of all, the I want to forward bias this, so that means I'm going to put the cathode connected to the negative of my source. Then I'm going to draw the cathode side of my diode. You can see it right there. Now I'm going to draw the anode side. See, there's the A right there. And there's my diode, forward biased. Now, remember, of course, why are we using the diode here? Well, we're using it as a solid state switch to control this load. And so here's my load resistor right there. And so what I'm going to do, I'm going to use some nice easy numbers. I'm going to make this DC source. This will be a, let's go with 10 volts. That way we don't have to get our calculators out. 10 volts. And over here we have a, here we have a load resistor that is going to be 2 ohms. And that pin is going to get retired. There we go, 2 ohms. Okay, so we have 2 ohms for the load. Now, according to Ohm's law, we should be able to have from this source, roughly speaking, about, I guess 5 amps, right? We do have to consider that there will be some voltage drop here. And so what really happens is with a 10 volt source, we would have a small voltage drop here of 0.7 of a volt, if it's forward biased. And down here, we would be left with the balance, which would be about 9.3 volts. And that's actually how you would calculate the amount of current. Now, because the barrier voltage is very small, in most line voltage applications, like in terms of 120 volts, things like that, we consider that voltage to be negligible, and so we don't include it in our current and power calculations. Okay, it's a very small amount, but as we get further into some of the other components, that very small barrier voltage can make quite a bit of difference in terms of some of our calculations. So I'll try to let you know as we go whether we really need to be concerned about calculating that 0.7 of a volt or not. Now, I want to talk about current flow for a moment. For the most part during this course, we talk about electron flow. And electron flow, I'm going to show like this. Electron flow would be from negative to positive. And so as I'm going to put polarities, let's put polarities on these as we go here. So that means I start from my negative. That means the cathode is going to be negative and the anode is going to be positive. Okay, and that's how we know it's forward bias. So negative and positive, and we're thinking about electrons moving through this from negative to positive. Now that current would then come down, flow through the load, making this end negative and this end positive, and then flowing back, of course, to the source. Now, one of the points that comes up with polarity in particular is that how is it that this piece of wire, which really connects to the anode here and to the beginning of this load, how can we have two different polarity marks there? How can this be both positive and negative? And so what I want you to carefully understand is that polarity always refers to the difference in potential from one side of a device to the other side. This polarity mark only makes reference to this polarity mark. So this side of the resistor is more negative than this side. This side of the actual diode is more negative than this side. Okay, so in terms of polarity, it always refers to just the polarity on the component that you're looking at. Now, is there another way to think of this? And so let's take a look. What about if we said, like they did back in the day when they started working with electronics, they said, you know what, we're going to have conventional flow, and we're going to say that current flows from positive to negative. Well, if that was the case, then we would have to say that, well, here's the positive terminal, so current must be flowing in this direction. And so I'm going to put an arrow with a C. I'm going to call that conventional flow. And what I want you to understand is that there's essentially no difference, really no difference at all. This is just a terminology thing, and it's something that just lives in your head, okay? Let me show you exactly what happens with potential. Here we have conventional current flow, which says that we're going to flow from positive to negative. So that means that we have current flowing in this direction. Now that means, what is going to be the current carrier in this type of current? Well, it's going to be holes, okay? These are going to be holes, and they're going to be going this way. Whereas here, we have actual electrons, and they're going this way. In fact, both of these things happen simultaneously. As the electrons are moving this way, the holes are in fact moving this way. But let's just follow through this example. Here's our conventional flow, and as it moves through the load, we see that we're coming from positive. As it arrives to the load, it's positive, and then it becomes more negative after it crosses the load. So that means this is positive, this is negative. Well, wait a second, that's exactly the same as it was in electron flow. In other words, this is positive and this is negative. Now let's move up and we go through here. That means that the anode, if the current is coming this way, the anode is more positive, and then the cathode is more negative, and then the current would flow back to this terminal. So that means that in fact, this is negative and this is positive. One is electron flow, one is conventional flow, and what you need to see is that in terms of polarity, absolutely no difference. And so if the polarity is not different, then how much does it really affect the way that we look at the circuit? And so what I want you to understand, not a big deal for you, nothing to worry about. We just need to realize that many times in electronic circuits, we're going to be using conventional flow, all right? Not a big difference. We're going to take a look at several of the applications that we have for diodes. And the simple PN junction, we call it a simple diode, has many, many applications. I guess the first thing I would say is that really most electronic circuits are going to employ diodes somewhere in them of varying sizes. But if you look at any printed circuit board with the components on it, you're almost guaranteed there's going to be some diodes in there somewhere. They serve many, many different functions in most electronic circuits. More specifically, we use individual diodes for things like switch selection. So we're using them as a solid state switch, sometimes to isolate chargers. If you have a couple of batteries that you need to charge, and you have one charger source, we'll use them for charge isolation to make sure that one battery doesn't discharge the other battery. They're used for polarity protection in circuits where an incorrect connection would prove to be a short circuit. We can use diodes for polarity protection to make sure that you can't mistakenly connect them with the wrong polarity. Power rectifiers. This is probably one of the largest uses of the simple diode, power rectifiers. We use them in single phase, and we use them in three phase. So they're used in any type of power rectification. Solid state AC to DC rectification is going to use these diodes. There are also some specialty type diodes, and I'll just add one at the bottom here. This is a little bit of a different type of diode. It's specifically designed, and it's called a Zener diode. Many of you will remember this from your studies of electronics in previous courses, the Zener diode. And so we're going to take a look at that, and we're going to look at a couple of examples of how that Zener diode can be used as well. Okay, first of all, we're going to start off by looking at the voltage and current relationship in just the simple diode, okay? Now the y-axis right here is going to indicate current. And this will be forward and reverse current. Our x-axis is going to be voltage. This will be forward voltage, and this will be reverse voltage. Now, one thing that you need to note is that the scale of the voltage on the left and right side of the y-axis is not going to be the same. And the reason is that over here, we know that the voltage, we want to look at how, as we apply forward voltage, what exactly happens with the current. And this is going to occur at some fairly low levels of voltage. So I'm going to make these divisions 0.2 of a volt each. Okay, so 0.2, 0.4, 0.6, 0.8, and 1 volt. Now, the diode that we would probably be using here would likely have a peak inverse voltage of about 600 volts. And so I'm going to put that right here on this line. Okay, this is going to be 600 volts. This will be 400 volts, and this will be 200 volts. So you can see the scale varies quite widely from side to side. Now let's go ahead and graph the current on here. So remember, forward bias is what we're going to be looking at on this side. Okay, so forward bias. And on our left-hand side, this is going to be reverse bias. So what does the diode do in terms of current? Now let's take a close look and see what happens. At 0 forward volts, there will be no current flow. So we can see the current would be at 0 on our x-axis. As it moves along, we start to increase the voltage. Not much is going to happen. But interestingly enough, by the time you get to about 0.5, you start to see a small amount of current that starts to move through the diode. Now, the diode, remember, is not going to actually close as a switch and conduct current until about 0.7 of a volt. But what we are going to see is before you get to 0.7, there will be what we call leakage current. So a little bit of current will start to actually flow through. And then by the time we get to 0.7, which is really right here, that current goes straight up and is only limited now by the resistance that you place in series with the diode. So if you don't have a proper resistor placed in there, this becomes short circuit current. Now, what happens if we reverse bias the diode? Well, we start increasing the voltage. We go 50, 100 volts, 200 volts, current still sitting at zero, absolutely no current. 400 volts, absolutely nothing. Now remember, the PIV of this diode is 600 volts. It blocks pretty much to the 600 volts, and then there's a sharp curve, and this was what we will call our reverse current, and it's also called avalanche current, in that it develops very quickly and normally destroys the device. Okay, so we don't want to press the voltage limitation in reverse too far, because when it gets to that point, it very quickly just breaks down, and that will be the end of it for the diode. Okay, the next thing we're going to take a look at is the Zener diode. And we're going to do the same graph, but for the Zener, and you're going to see some kind of interesting things about the Zener diode, because it does react like a diode in many ways, but it has some very special characteristic. Now, the Zener diode is going to have a very similar graph. Okay, we're going to have current both forward and reverse. And we're going to have voltage both forward and reverse. And the main difference with the Zener diode is that the reverse voltage, what we would have called peak inverse voltage when we were talking about a simple diode, that peak inverse voltage has a different name with the Zener diode, and here it's called the Zener voltage. So we're going to graph the Zener voltage on the left-hand side. So over here we have Zener voltage. On this side, we have just the normal forward voltage rating. Now, the forward voltage rating of a Zener diode, interestingly enough, is pretty much exactly the same as a simple diode. In other words, 0.2, 0.4, 0.6, 0.8, and 1 volt. And if you were to connect this diode in the forward bias, it would actually act exactly like a normal diode. The only problem is that it does not have a strong reverse voltage, so you can't actually use it in that way. Zener diodes are connected in reverse bias. Okay, Zener diodes are connected in reverse bias. That's their normal mode of operation, is the reverse bias. For our example, I'm going to use a 32 volt Zener diode. Okay, this is going to be a 32 volt. Now what that means is that its forward voltage will be about 0.7 of a volt, just like a normal diode, but its reverse voltage, where it actually starts to conduct, is going to be 32 volts. Now this is in fact its operational voltage. This is the voltage that we're actually looking at with this, and in terms of the applications, that is the exact voltage that we would want it to start to conduct in the reverse direction. And so we could say this would be about 16, 24, and 8 volts there. So that would be the scale. Now it's still a different scale between reverse and forward, but not nearly the spread that we have in a normal PN junction. So let's take a look and see what happens to current. Obviously in the forward It would operate exactly the same as a regular diode. But here's the interesting thing. When we hook it up in reverse, it blocks, and then when it gets to 32 volts, it starts to conduct. Now here's the thing. It does not self-destruct at this point. This is normal operating current. And as long as we maintain this current at a level that is within the ratings of this Zener diode, absolutely no harm will come to the diode. So these diodes will have a voltage rating and a power rating. And from between the voltage and the power rating, we can determine what their actual rated operating current, their safe level of operating current is. Okay, what I'm going to do is I'm going to show you a couple of examples of how the Zener diode is used. The first circuit is actually a regulator circuit. So the Zener diode is used with a DC source to provide an absolutely regulated even voltage to a load. Let me show you how this will look. What we'll do is we'll start with a DC source. And I'm going to give you, just as an example, let's say that this is a 0 to 20 volts variable DC source, all right? What we're going to do is we're going to come along. Now, as we build this circuit, we are going to need a resistor that will be just in the line right there. And this resistor is there just to drop voltage, actually. So it's called a dropping resistor. And then we reach the point where we put the diode in. Now, what we're going to do is I'm going to make this my negative and positive. Now remember, I'm going to hook up my Zener diode first, and it's going to look like this. Reverse bias, okay? Think reverse bias. So that means here we have the negative that needs to go to the, normally it would go to the N-type material. In this case, we want it to go to the P-type material. So I'm going to draw my A first. I know that's the P-type material. Now I'm going to put the K on the other end. Now a Zener diode also has a couple of small angled lines on the end of it, and there is your Zener diode. And it is connected reverse bias. This resistor will prevent any short circuit, but also as this voltage of the source rises above the Zener voltage level, this will actually take and drop the additional voltage. Now, as a regulator, what we do is we place in parallel with the Zener diode the load. And this is the regulated load. Now, let's just walk through this and see how this works. I'm going to give this Zener diode a Zener voltage, E Zener, of 10 volts. Okay. Now, what that means is that this diode will block until we pass 10 volts. So as this source voltage rises, the current will start to flow through the dropping resistor. If we don't have 10 volts, we don't have enough to actually make this open and act like a, let current through it. That doesn't happen until 10 volts. So if we're at, say, 6 or 7 volts, that voltage will simply be shared between this dropping resistor and this load resistor. Once we reach 10 volts, something interesting happens. This now actually begins to conduct at 10 volts. So we take our source up to, say, 12 volts. This voltage stays at 10 volts. And because this regulated load is exactly in parallel with that, this voltage stays at exactly 10 volts. Once we have exceeded and surpassed the 10 volts from our source, the regulated voltage will remain at 10 volts. What will happen though is that as we increase our source voltage, say to 12 volts, we would have 2 volts here and 10 volts here. As we if we took this up to 18 volts, we would have 8 volts on our dropping resistor, still 10 volts here, and of course 10 volts on the load. So we maintain that exact 10 volts on the load because of this Zener voltage. Now, what changes obviously is as we increase our source current, the total amount of current in the circuit is going to rise. The regulated load voltage has to stay the same because it's the same size resistance and the same voltage all the time. So what's going to change? Well, our Zener current will rise as source voltage rises. Now, at some point, we will actually exceed the current rating of this diode. And so when we work these circuits out, we look at the amount of power that can be dissipated by the Zener, and that will actually limit how high we can turn this source voltage. So we'll be looking at some of those examples as we go along. This is the Zener diode used as a regulator. Okay, we're going to do a Zener regulator example problem now, and you can grab your calculator and work through this with me. As I draw it, you'll see what you need to calculate as we go. We're going to start here with a DC source, and this is going to be 0 to 12 volts. 0 to 12 volts. So this is an adjustable voltage source. We're going to use electron flow in this particular example. I'm going to make that negative positive. Show you the electron current flow there. Now, as we go ahead, we're going to have a dropping resistor here. I'm going to tell you the size of this resistor. This is something we can calculate in different problems, but in this case, it's a given. This is 5 ohms. Now what we have is in reverse bias, anode, cathode, and there is our Zener diode. Now, exactly in parallel with that, we have the load, and this is the load that actually needs to be regulated. In this case, this is a 500 ohms load, and it needs to be regulated. And so what we're going to do is we're going to place a Zener diode with the actual voltage rating, the Zener voltage rating that we need to maintain across the load. And so what it is actually, we're going to use a 5-volt Zener. Now what that means is that we want no more than 5 volts here. So once we pass 5 volts on our source, we know that the load voltage will not go higher than 5 volts. Now, the Zener diode itself is a 5-volt Zener, and it's rated for 4 watts. The first thing that we would like to do is let's go ahead and make a note of the question. There's a couple of questions that we want to solve for. And so I'm going to start with question number 1. Question number 1 is, let's find the current of the Zener diode, current of the Zener, and the power of the Zener when the source is adjusted to 7 volts. So with 7 volts DC, what is the current of the Zener and the power of the Zener? So let's go ahead and work through this. Now, if the source is set to 7 volts, what that means is we can see that this is really going to be 2 volts here and 5 volts here across this parallel branch, which includes the Zener diode and the load, 5 volts there. The way that we deal with current is like this. The actual load current is pretty straightforward because we simply look at the 5 volts and the 500 ohms. And here's where you're going to need to grab your calculator, and you come up with 10 milliamps. Okay, 10 milliamps. Now that 10 milliamps will only drop below 10 milliamps if the source voltage drops below 5 volts. So if we drop down to the point, let's say, where we only have 3 volts applied here, well, then what we would have is just a series circuit. We'd have to calculate the current. We'd have some voltage drop here and some here, and it would be a smaller current. But once we hit that 5 volts and this starts to conduct, this stays even at 10 milliamps. Now, at 7 volts, what we need to do is we need to take a look and say, what will the actual voltage be through this dropping resistor? And so we're going to grab a calculator here, and we're going to work that out. All right, so what we have here, 2 volts divided by 5 ohms, and what we are going to see here is 400 milliamps. 400 milliamps. Now, if 400 milliamps is moving through this dropping resistor, only 10 milliamps flowing through the load, that leaves us with, in this case, 390 milliamps. And if you take that 390 milliamps and you multiply it by the voltage, that equals 1.95 watts. So still well within our 4-watt rating. So that means that this Zener is definitely completely capable of regulating that load voltage to 5 volts with even more source voltage. Okay, the next thing we're going to do is we're going to find the maximum source voltage that we could actually use without exceeding the power rating of the Zener diode. Now let's take a look at how we do that, the maximum source voltage. First of all, I think what we need to do is we need to say, what is the absolute largest amount of current that this Zener diode can actually pass? And in fact, all we need to do is look at the voltage of the Zener and the power rating, and we can quickly determine that this is actually limited to 800 milliamps. And that means that the total circuit current coming from this source through this dropping resistor could be as high as 810 milliamps. Now, how is that? Well, 800 for the Zener and 10 for the load. So a total of 810 milliamps. Now, let's go ahead and we'll take our calculator again, and we want to find out what is the voltage across this dropping resistor. And if we add that to the Zener voltage, that'll actually be the total voltage that we can have from our source. So we want voltage 0.81 of an amp times 5 ohms, and it equals 4.05 volts. 4.05 volts. Now, if we have 4.05 volts being dropped on our dropping resistor, obviously 5 volts being dropped across the load and the Zener, giving us our 800 milliamps, then we look at it and we go, okay, that's at its capacity. That actually makes 4 watts. That's as high as we can have there. So that means that the highest that we can actually run our source voltage to is 4.05 plus 5, or 9.05 volts. That would be the highest voltage that we could adjust our source to. And that gives you a little bit of an idea of how the Zener regulator circuit would work. Okay, the last example in this particular section is going to be using the Zener in what we call a clipper circuit. And this is a real interesting one because one of the components that we're going to be looking at a little bit later when we get into thyristors um, is called a diac. It actually very closely relates to this particular circuit. And so this one's a good one to pay attention to in terms of foundation for further components. All right, with the Zener clipper circuit, something interesting happens, and this is the way that we typically use it. Imagine that you have here a single phase circuit with a 120 volt supply, 120 volts. And over here, we are going to hook up your favorite big screen TV. Okay, and it needs 120 volts. And it needs it to be actually pretty steady and pretty clean. So what we do is right here, we're going to place not just one Zener diode, but actually two. But we're going to place them in what we call an inverse series connection. Inverse series. So let me make a note of this. Inverse series. So there's our two Zeners. Now, if you think about this, let's say that at a moment in time, this was negative and this was positive. Now, this is an AC source, so we know it's going to be going back and forth 60 times a second if we happen to be at 60 hertz, which normally is the case in North America. So here we have, let's say that we had negative, positive. Now, this negative would be connected to this Zener diode in what we would call reverse bias, because it looks like the negative goes to the anode, which is P-type material. So this would be reverse. And then this one, the negative would actually be connected to the cathode because they're at the same point in time. So this one would actually be forward. So what that means is that this one would not start to conduct until it reached its Zener voltage because it would be reverse biased. This one, all it would only take would be 0.7 of a volt and it would begin conducting. But because this one is here, we're well past that 0.7 of a volt. The moment that this one starts to conduct, this one will easily conduct, will be way, way past the 0.7 of a volt. Now, if we were to take and make our polarities opposite on the other side of the sine wave, right here, now what happens is this one would be negative to anode, which would be reverse biased, and this one would be forward biased. And so in the same way, this one will block until the Zener voltage. Once it does conduct, this will easily conduct because it only takes 0.7 of a volt. Now, how does this work in the circuit? And let me show you the waveform that you would see under normal circumstances at this point. You would see a waveform that should look like this, coming along like this. Everything nice and even. If this is a 120 volt source, we know that this would be about 170 volts positive. This would be 170 volts negative. Now, we don't want these Zener diodes to do anything as long as our voltage is at a nice even peak of 170 volts. But here's the problem. Let's say that we get a strike of lightning out on the line, and all of a sudden this voltage shoots well in advance above that peak, and it goes down here. Now, in fact, this could be much higher, many, many times higher than the 170 volts. But what we want to see is what happens in this case. As soon as the voltage at this point is rising, when it gets to 170 volts, this Zener diode with a 170 volt Zener voltage will start to conduct. And so that means that what we would really see on this waveform would be the voltage rising, then going straight across and clipping off that surge. Then, as it comes to the negative, it would rise this way in the negative direction, and it would come across this Zener diode, and this one would start to conduct, giving us basically a chopped off line at that 170 volts. What we call this is a clipper circuit, otherwise known as a surge suppressor. And so the two Zeners, because of the way that they operate, they begin to conduct, and they basically flatten out and cut the top off of that waveform. And essentially taking, especially for electronic equipment, computers, TVs, things like that, we like to make sure that we don't have surges on those types of equipment. Very, very damaging. All right, that pretty much wraps up this particular segment. And now that we've looked at the diodes, we've looked at the simple diodes, we've looked at Zener diodes. The very next thing that we're going to move into is how do we use simple diodes for power rectification. And basically, this is one of the largest areas of use for basically PN junctions. Lots and lots of power rectifiers out there. I'm going to show you several of the different forms, and that's coming up next. All right.